Hello, everyone. Paul here to show you how to do the plate tectonics exercise. We're not going to do nearly everything, so don't go. Oh my gosh, there's so much here. No, 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 no. We're just going to do section 2.3, part A, 1, 2, 3, 4, skip 5, and then 6, and then part B, 1, 2, skip 3, and do 4, and then 2.7. A and B, just everything there. Don't worry about, oh my gosh, I need to write all this down. It'll be in the Dropbox instructions, so you'll have that. So let me show you how to do this. And so my apologies for my lousy photography here. If I can get the slide to switch, there we go. Normally I would scan this, but I don't have my scanner on me. So this is that first section, and it's dealing with the Hawaiian Islands and the Emperor Seamount chain, and calculating plate velocities based on some information about that. Now, it will really help if you have watched my lecture on plate tectonics, in particular the parts about Hawaii and the Hawaiian hotspot, because I kind of lay out how all this works. Um, I've gotten emails from a couple of you who aren't in the class and therefore don't yet have access to the lectures. That's fine. By the time I post this, you will notice that there are links to the lectures on plate tectonics in the from the lab course shell, so that you can go back and watch those. In particular, like I said, you want to watch the part about the Hawaiian Islands. I'm going to kind of assume that you have. I'm not going to kind of go through all that again, but we have a hot spot and we have a tectonic plate moving over it, and we can use that then to calculate the plate velocity, and I'm going to show you how to do that. So first of all, they ask if both the Hawaiian Islands and the Emperor Seamount chain are over the same hotspot. What is the possible reason the hotspot changes about 42 million years ago, right? And they're referring to the idea here that up here, the Emperor Seamount chain is aligned more or less north-south, whereas here, the Hawaiian Island chain is kind of northwest-south east, and about 42 million years ago is where that kind of switched. So think about plates moving over hot spots and whether they always need to be moving in the same direction or not, something like that, maybe, I don't know. So anyway, think about that a little bit. But let's get down to calculating the velocity, right? And by the way, if you do watch my lecture, I tell you how to deal with number one if you're still confused. So anyway, let's think about plate velocity. Okay, so they ask, what's the rate of Pacific plate motion relative to the hotspot as it was developing along the 2,300 kilometer long Emperor Seamount chain from 65 to 42 million years ago, and express the rate in centimeters per year. And then what direction was the plate moving relative to the hotspot during that time? Okay, so we want two things. We want speed and we want direction. Okay, so if I go back here, so if we think about this, speed, any kind of speed, is distance divided by time, right? Miles per hour, meters per second, parsecs per fortnight. I don't know, whatever. Okay, it's how far did you go and how long did it take you to get there, right? It's that simple. So that's what we need. We need a distance and we need a time. Okay, so we're talking about here between 65 and 42 million years ago. So that's the distance right there. But how far is it? So when I first read this, I was like, well, shoot, they don't give them a map scale. How are they going to know how far that is? But then I read the question again. Let me go back. And they tell you 2,300 kilometers, right? They tell you the distance, okay? So that's what we're going to use for distance, right? That 2,300 kilometers. There we go. So there we go. Now we need to divide that by time, right? So what we need to know is how long did it take, an island to traverse this distance, right? Well, we know that this island down here is 42 million years old. We know that that island up there is 65. If I subtract those two, that gives me the time. right? And so we set this up like that, right? Where I subtract the 65 from the 42, and then I divide it by 2300. Simple enough, okay? Um, so once again, we got our distance because they gave it to us in the question, 2,300 kilometers, and then we have our time by subtracting those two, right? So it took this island, this little seamount up here, that much time to go from there to there, okay? And so that's going to give us an answer. Now, do the arithmetic, you'll get an actual answer here. But here's the thing. Um, And that thing is that if you divide, this is millions of years, okay, and this is kilometers, okay. So when you divide this, the unit you end up with is kilometers per million years. First of all, that's not the unit they ask for. They say centimeters per year. And the reason they say centimeters per year is kilometers per million years is a useless unit. Okay. No one knows how fast that is. If you say I'm moving 200 kilometers per million years, great. Okay then, so don't yeah, no. Now we could go through some fancy dimensional analysis to figure out how to convert kilometers per million years to centimeters per year, but I'm going to save you a lot of time. Divide by 10. That's all you need to do is divide by 10, okay? Or even if you don't even want to divide, that's fine. Move the decimal one place to the left. Okay, so for example, if you got 76.2 kilometers per million years, sorry, that ends up being 7.62 centimeters per year. It works that way. Okay, for plate tectonic velocities, you should expect to get something, maybe between 3 and let's say 15 or so centimeters per year, something like that. If you're getting hundreds of centimeters per year, you did something wrong. If you're getting less than one, you did something wrong. Okay. I'm not dying. I just need a little bit of water. So yeah. So expect to get something, let's say between, in the range of 10, 5 to 15 or something like that. Okay. Now, let me go back real quick here. And so they ask about direction, and let me give this away. Too far. If you watch the lecture, you know that when we're thinking about the direction that these plates are moving, bear with me, I'm going to draw. That if I draw an arrow from the younger rock to the older rock, that's the direction the plate's moving. Pretend that's an arrow. That's the direction the plate's moving. So in this case, it's moving to the west, and that will always, always, always work. If you draw an arrow from the younger rock to the older rock, that tells you what direction that tectonic plate is moving over that hot spot. All right. Okay, let me try this. No, it doesn't work that way. Okay, fine. There. Oh, nope, too far. Okay, so let me see. So Hawaiian hotspot 2300, great. And then what rate was the Pacific motion to the Hawaiian hotspot from 5.1 to 0.8 million years expressed in centimeters per year? Now this is going to not involve this map, but now we need to go to this map. So they say between 5.1 and 0.8 million years. So that's between the formation of Kauai. Let me get out of my pen here. That's between the formation of Kauai up here and Maui down here. Now we have the same thing we had before. We have the ages of these rocks. They're igneous rocks, so we can radiometrically date them, so we know how old they are. So we do the same thing you did before, that 5.1 minus the 0.8, and that will give you the time. Now we need the distance, right? And they didn't tell you the distance, right? But you've got a map scale. Okay, so what I would do, lay down a piece of paper, make your little tick marks at, 30, 60, 90, 120, 150. Then you can move that piece of paper around. I can just kind of guesstimate that's about 150 kilometers. There's about another 150 kilometers, so that's 300 kilometers. There's another, I don't know, I'm getting about 450. You might get more, you might get less when you do it more precisely, right? So about 450 kilometers. There's our distance, right? That 5.1 minus 0.8, that will give us your time, right? Speed is always distance divided by time. So divide the distance that you get using the map scale by the times that you get by subtracting those numbers, and that'll tell you the speed that it's been moving since that time, right? And then they have you do the same thing from, let me see, Loihi, Hawaiian hotspot, plate motion relative from 0.8 million years old to today. Same thing over and over and over again. Okay, so, either, use the map scale to measure the distance, use the ages of the rock to work out the time, and then that will give you the speed. Okay, same thing with the Yellowstone hotspot. We have you doing the same thing here. It's up here in kind of Idaho, Wyoming area. And these are ancient volcanoes with their ages in millions of years. Here's a map scale here you can use to determine distances. So when you're answering those questions, use the map scale to measure the distance, subtract some numbers to get the times. Bingo, there's the speed. Okay, speed is always distance divided by time. It just is. Okay, and then the last thing I have you do concerns the area on the west coast of South America, which is a nice classic ocean continent convergent plate boundary. And so the first thing they ask you to do is use a red pencil. I don't care if it's a red. If you just use a regular black pencil, that's fine. Okay, to trace out the plate boundaries and then label a couple of things. And you've got in your lab manual a map of the plate boundaries with things labeled. So if you look at this area, it'll show you where those things are. Like the Galapagos rise and things like that. So anyway, though, so first of all, this part of the boundary is easy. There it is right there, right? The boundary between the Nazca plate and the South American plate, and then you can just kind of draw your line, along these volcanoes, right? Or rather, these earthquakes, not volcanoes. These earthquakes, right? That's where the plate boundary is, right there, up through, the middle of that little oblong cloud. Go either way here. It gets a little hinky here, but that's okay. Anyway, right through that oblong cloud of earthquakes. And then they have you do something, and I just think this is fascinating. And I know, spend your lives with professors thinking things are fascinating that you're like, what the heck? But this is really very cool. So what they've done here is they've taken a cut from B to B prime and laid it out here. And then what you're going to do is you're going to graph the earthquakes and volcanoes along that line, and they do it with the depth going this way, right? So what you're doing here, and geologists, we do this a lot, okay? Graphing something as you go down through the earth, because it gives you a picture of it the way it actually is, right? If you graph the depth going up, then it would be upside down. Okay, so we like to do this, and so here's the trench right here. Okay, so that point right there on the B prime line is right there. So there's a few earthquakes to the west of the trench. And so, they tell you 200 kilometers, 20 kilometers down. So 200 kilometers is over here. Sorry, there's the zero line. So, and then 20 kilometers down. Well, that's 100 there. 20's, I don't know. My mouse isn't even that sensitive. Right there. Put a point there, right? 160, 25, 150, 160, 25 is, I don't know, a little higher than that, anyway, put a point right there, etc., etc. right? Just a few to the west. Most everything is, the fun stuff is to the east of the trench, right? Because here we go through this volcanic mountain range, and you can see we got some very deep earthquakes back here. Deeper as you get this way. Watch the lecture; it'll explain why. Okay, and then you also have volcanoes and earthquakes, right? So 330 kilometers, there's a volcano, awesome. 330 kilometers, maybe right about there, there's a volcano. Draw a little triangle there, or something, little V for volcano or whatever you like. And so plot the volcanoes and plot the earthquakes. Now, when you're done, what you're going to get is you're going to have a few shallow earthquakes here. You're going to have a few shallow earthquakes along here. And then you're also going to have some volcanoes along here. But then you're going to have a bunch of earthquakes that go down, okay, following that subducting plate down into the mantle. So you're going to have a bunch of earthquakes that go down. So you'll have earthquakes over here, shallow earthquakes over here, shallow earthquakes over here, along with some volcanoes, and then deepening earthquakes coming down like this. Okay, and then once you get that done, you'll be in a position to answer the questions, what depth does things happen, and you should be good to go. Okay, alrighty, so I am going to go and I'm going to render this video and I'm going to upload it to YouTube. I'll get it in along with the videos from the lecture, and I'll get everything set up for you guys so that by the time you're seeing it, everything should be ready to go. All right, okay, okay. If you have any questions, get with me. Definitely get with me if you have any questions. Okay, okay, bye-bye.